Well, thanks everybody. It's great to be here. I've travelled a long way, but some of you have come a lot further than me. I just came from Auckland a couple of days ago. So I just wanted to see a little bit more about the audience. How many of you have been doing XR for more than 2 years? Can you raise your hand? Okay, keep your hands up if it's more than 5 years, more than 10 years, more than 15 years. And Frank has got his hand up, Gwen. So I've been in the game for a long time. My first VR experience was in 1989, so 27 years ago. And you can see this is virtual Seattle, so this is a very blocky environment. And we used at that time the VPL system from VPL Research. We had connected the VPL iPhone, you can see at the top there, which is 230 by, or 320 by 280 or 240 pixels. And in today's dollars, that would cost you $28,000. We had a data glove so we could capture a real hand input, and that would cost about $23,000 today. We used a fiber optic cable, and then we connected that to a Silicon Graphics Onyx computer that's about $650,000 today, which is about the same price as a house in Adelaide. And you can see on the right-hand corner, this is the very first virtual environment that I built myself, very abstract. And because we had this budget of 1,500 polygons, it was really, you couldn't do anything with that. So one of the goals of VR, as you know, is to try and capture more natural input. And in those days, we had gloves, and we started using handheld controllers like you have with the Vive and things today. But one of the first projects I did when I started my PhD was also look at how you could add more natural input. And so this is a project we did in 2002, and it was using a very early depth sensing camera that we basically glued to an AR headset, so you could use your natural hands to reach out and touch virtual content. And you can see in the top right-hand corner and the bottom right-hand corner, we're using a pen. So it used a depth-based segmentation, and whatever objects you put or have hand input you could use to make more natural input. But that was very, very early days. So since that time, people have tried to do research on how to make hand input much more natural in VR and AR. About 10 years ago, we were gluing things to head-mount displays, and then in 2013, Meta, the other Meta, not the big Meta, came out with the Meta AR head-mount display, Meta 1, that was a headset with basically an integrated depth sensor into it. And then Leap Motion made their hand tracking hardware, you can still buy that today, and a bunch of people glued that on the front of Oculus displays. And then the Quest came out in 2019 with their own hand tracking. So it's really only been 5 or 6 years that we've had untethered hand tracking that lets you have really natural input into VR. And similarly with eye tracking, in 2016, the Samsung Gear worked with a company, German company SMI, to integrate that into the Samsung Gear head-mount display, which had the mobile phone. But that would cost you about $15,000 to buy in those days. And then a couple of years after that, Apple acquired SMI, and so nobody could buy that anymore. And of course, in 2017, Fove was the very first commercial VR display with eye tracking in it. And then Vive followed thereafter, and then Pico, and now, of course, the Quest Pro as well. So we've had this effort to move towards more natural eye gaze input as well. And then the final trend I want to talk about is physiological sensing. So 7 years ago, in 2018, a group at MIT had the idea that they could put a bunch of physiological sensors, like heart rate sensors, and combine it with a HoloLens 2. And then a couple of years later, you started seeing some commercial products come out, the Lucid VR from Korea, the DS1 from Germany, and then and they both supported EEG to measure brain activity. And then in 2020, HP created the Reverb, which could measure heart rate. It wasn't a big success, but it was one of the first examples of an integrated heart rate sensor into a VR display. So you can see there's these kind of key phases in intuitive input. For the first almost 20 years, we were using gloves and handheld controllers, and then suddenly we could use our hand gestures with nothing, and then we had the eye tracking, and now the last 5 or 6 years, we're starting to look at how we could use natural brain input and heart rate sensing inside these displays. So overall, the trend has been from explicit to implicit input. So when I first started doing the VPL, it was really about active pointing and grabbing objects and using controllers. And then where we're at currently now is we've got freehand input and then we're moving towards now eye gaze and brain activity. So it's really going from explicit input to implicit input, where the system now can know what we intend to do by monitoring our brain activity, measure our stress with heart rate and things like that. The other important trend, though, is, and so just to have a slight sidetrack, the state of the art today is a couple of displays. Galea is from OpenBCI, and this is a headset that combines EEG, gaze tracking, heart rate, and with VR headsets, you've got this very nice faceplate that you push against your skin, and so Galea puts a bunch of different sensors inside the faceplate. And so that's an example of a VR all-in-one system. And then the bottom, Cognition makes an AR all-in-one system with EEG electrodes on the back and also electrodes for heart rate and other things as well. And so here's a bit more about the Galea. So there's the faceplate with the sensors in it. There's 11 integrated sensors. Then across the top of the head, there's EEG, and at the back of the head as well. And that can now allow you to do a wide range of different things. You can see here you can measure things like cognitive load from skin temperature. You can measure your heart rate for stress. You can measure your arousal level, face expression, and attention, and so forth. So what that means is that we now can move beyond the human ability to detect information about people in front of us. We can do things like health monitoring. We can detect and measure emotional states. The picture on the left-hand side is using an infrared camera to measure when you're feeling frustrated or not. We can measure attention and focus, and we can measure brain activity. The picture in the middle is a brain activity monitor as well. So as an example of that, this is one of the projects one of my students worked on a couple of years ago. And in this project, Empathic XR, the idea was to be able to see other people's emotions. So you can imagine in a meeting with somebody, you're talking to them, and you've got your mixed reality display, and then around them, you can see this aura, and the aura changes color depending on your emotional state. So it uses AR to show the emotional state, and it uses an ECG sensor to measure your heart rate. So here's a video of it working. So they're playing a game, and you can see around the person is this aura that changes color depending if they are feeling stress or relaxed. And so there's the ECG sensor. You have a neural network. You map onto a color wheel with arousal and valence, and then you map those colors around the person. And this is shown inside the HTC Vive head mount display. So, unfortunately, though, the Galea is very expensive. If you want to buy a Galea today, it's $35,000 for starting price US, and then you have to add on to that. If you want video pass-through, it's another $5,000. If you want more EEG sensors, it's another $15,000. So it's expensive. So you can imagine the XR display of the future. There's unobtrusive glasses like this. It can provide you AR, VR experiences. It has physiological sensing. It combines with AI as well for emotion understanding. And yesterday you saw some examples of Snap of a pair of glasses that's almost like this. Now that may sound a bit far-fetched, but all the components are there already. So you've got the Orion display that Meta has shown that has a very wide field of view, and the input band, which is now part of the Ray-Ban display glasses. You've got the Aria system that Meta also produces, which has eye tracking, heart rate sensor, IMU, GPS, and cameras. And then you have the Athena from Muse, which is a headband that lets you measure brain activity, EEG, but also FNIRS. FNIRS is the blood flow at the forebrain, so you can measure cognitive load. And you can imagine gluing these together. This is about $400. This is not for sale. This is going to be about $10,000. But in 5 years' time, you could easily imagine that could be around a couple of $1,000 or less. So let's imagine what we could do with that. And there's a wide range of examples, and I'll talk about a few of them today. You could imagine new types of training, gaming, building agents, and so forth. So one example is, which we're doing in our lab, is looking at input preference intent. So here's the Magic Leap 2 display, and like many displays, you've got a number of different options for input. You can use the handheld controller, you could use your free hands, or maybe you've got a Meta band and you can use gesture recognition. So there's several possible devices, and depending what you're doing, you may want to change the input device. So the question is, how can you detect when somebody wants to change their device they're doing to make the user interaction more natural? So in this project, what we looked at doing is, could we measure using EEG the person's input preferences, and so we can then know when we should allow them to change input device. So we had the system set up here where the person was using either a handheld controller or a gesture, and they did 3 basic tasks: a pointing task, a manipulation task, or a rotation task. And while they did those tasks, we measured their brain activity. So here's the pointing task, and there's the manipulation task, picking up an object and putting it in here, and here's the rotating task. This is with the freehand gesture, but we did the same tasks with the handheld controller as well. And then what we did is, it's a bit complicated, but we did the experiment design where we had them doing the tasks with low and high complexity, and we would measure their brain activity while they're doing that. And then after each task, we'd ask them if they wanted to change input device. And we could see if their desire to change matches the brain activity. And I won't go through the whole paper, but here's the top-level summary. Basically, what we showed is that we could recognize with 86% accuracy people's intent to change from the EEG signals. And this aligned up with their actual subjective wishes. And we also found that the EEG measured right after that they'd completed the task. The 3 seconds after was the most important period to measure that intent. And then we also looked at the power spectral density, which is a way of processing EEG signals to find which was the best feature processing that was most accurate, and was that one as well. So that's one example of how, if you integrate sensors into a headset like this, you can then start having more interesting interactions. A second example is around trust. So those of you who've been in, you used your phone for driving in your car, or maybe you have been walking around the streets. There's lots of examples of people who've been guided by Google Maps into a paddock or in somewhere. So how do you know you want to trust the agent that's giving you directions? And so, how can you reliably measure trust? So we did a project looking at how can we measure trust from these physiological signals. Previously, people would have interaction with an agent, and then they'd have a survey at the end. Do you trust this agent or not? And they'd say, yes, I trust it or not. But we wanted to see if we could use the EEG and the GSR, which is your skin sweating, and your heart rate variability to evaluate trust at different levels of cognitive load. And you can see in this picture, the different boxes here, these are all different pieces of hardware we had to glue together. So this was done before the Galea days, and this was showing you one of the downsides of this type of study, and it's very complicated to connect all the sensors together. And so that's why integrated sensing is very important. So we had people do this task, very, very simple. They had wearing all the gear. In the VR display, in this pink box, they were shown a target. There's a red box there now. And the goal was to look around to try and find that target. And the scene was full of other distracting objects. And then there were basically 3 different conditions. One condition was you just did it by yourself. A second condition was you had a voice in your head that would tell you to look left or right. So you could leave look left or right. And that was, the voice would always tell you the correct thing to do. And the third condition was that the voice would lie half the time. So it would say, look right, and then actually the target was closest to the left. So, of course, after you tried that third condition, you learnt to distrust the agent. And what we found, so here's the kind of experiment set up. You had low and high cognitive loads, so you had more or less distractors. And what we found was interesting was that actually by using the EEG signal, we could, by using the alpha band power, which is a measure of overall brain activity, that correlated to different levels of cognitive load. So that makes sense. If you have a harder task, you're thinking more about it. But by measuring the GSR and the heart rate, there was a significant difference in this little peaks here, depending upon if you trusted the agent or not. So this is very early days, but this shows us that potentially you could use physiological cues like this to measure trust. And if you can do that, you can do that while people are in an XR environment or VR environment, and you can change as well. So if you're interacting with an agent and the agent starts to detect you're not trusting it, it may be more truthful or provide different feedback to build that sense of trust again. So that's 2 examples. So this is an example of using that technology to understand your state. The second thing that's really interesting is about using this technology to increase collaboration, enhance collaboration. So here's one example of that. Here's a teaching scenario. So we've got a teacher who's trying to teach somebody in VR, in this case, how to assemble a motor. So there's a person with a motor. But because we've got this gear to measure their implicit cues, we can measure their brain activity and attention. And so above the person, above their avatar, there are these icons here showing if they're having a high cognitive load, if they're paying attention, and their heart rate. So if I'm a teacher, I can be in the VR environment teaching, and I can look at my student, and I can see whether or not they're having a hard time or not paying with the class. So we did this a couple of years ago, and here's the video. First of all, we had to use an NBAC test to measure your cognitive load capacity. So some people have more or less cognitive load, so we can measure this and then set a baseline. And then inside the VR environment, there's the person with the icon above their head, and we can now have them do this assembly task, and occasionally we'll look at their head and see above their head whether they're having a hard time or not. So you can see in just a second, the person has a red above their head, now just turned to yellow. So they're finding the task hard, but now they're turned away to find it easier, because now they're going to pick up an object, which is very easy to do. And what we found from that was that people, the teachers, really preferred being able to have this ability to monitor people's cognitive load and also their attention, so they could tell whether or not the person's paying attention or not. So that's one example of how you can use this to change collaboration. Here's a more fun example. A couple of years ago, we made a game called the Neural Drum, and the idea was you could go into mixed reality, take some everyday objects, and start drumming with these objects across the table with your friend. And you would see your friend across the table, and as you started drumming, when you do activities like drumming, sometimes the brain activity synchronizes, the electrical signals in the brain synchronize. So as the synchronization increases, then the real world fades away and becomes a purely virtual environment. So you can see here, you can see your friend across the way, and as we get into sync, it fades away. So what we did is we had this HTC system, we have 3 electrodes just across the front brain, drumsticks, and then both people started drumming, they were connected to the same laptop, and we measured the phase lock value, which measures the difference in phase between the signals. So here's a video of the system working. And this was shown at the SIGGRAPH Asia conference a couple of years ago.
Neural Drum is a VR drumming experience that allows 2 players to drum together while their brain signals are simultaneously measured. At first, you can set some daily objects on a table to use as drums. A player will use 2 drumming sticks to play the game. Both of the players will wear an EEG capturing hardware to get their brain signals measured from the frontal lobe. The data acquired will be streamed to the data processing system to enhance VR experience, depending on the player's collaborative performance. We designed a software to calculate the phase locking value, which is an index of neural synchronicity, for the FP1 and FP2 channels of the theta band from both the participants. When synchronization between 2 players is low, the camera will be more clear to do so, whereas when synchronization is high, the vision becomes more obscured, with each point cloud eliciting higher particle effects. We logged and analyzed the user's brain signals, as well as had them answer a subjective questionnaire regarding their perception of synchronicity with their partner and the overall experience during a pilot study. We discussed design.
Okay, so this is an example of the results. So here's 2 people playing, and this is not a very good player. So the green bars are when they're hitting in time to the other person, and the blue line here is the phase locking value, and it's kind of jagged and not very smooth. And on the right-hand side, you can see more common blue bars, so they're hitting in time with each other, and now the blue line is much lower amplitude. And you had comments like this, it's quite interesting. I actually felt like my body was being exchanged with my partner. So having that brain synchrony creates these special effects. So the last thing I want to talk about that fits into this is we've talked about being aware of yourself. We've talked about creating collaborative activities with somebody else. The most important thing also is being able to do this experience capture piece at the end. So we're doing some work in our lab around being able to capture your surroundings and combine that with AI and physical AI to understand what's happening in the surroundings as well. And you can do that by using clusters of these RGBD sensors, and you can fuse together the point cloud to create a real-time map or model of the real world. So here's one example of this. We had two people doing a task. One person in AR was looking at moving real blocks in the real world. We surrounded the table with some depth sensing cameras, captured that, and then live streamed it to a remote person who could collaborate with them. And then when this person makes movements, the remote person will see it, and their hand is put into the mixed reality environment to guide them as well. So you can see here on the left-hand side is the AR view. The blue hand is the person at VR here moving the object, saying moving the yellow one, and then the person picks it up, and you'll see in a minute he'll put it down on the table, and the yellow object will appear on the table in the real world, and then the person in mixed reality or VR can tell him to position it as well. So this is a very natural way to collaborate, and you can now, because you have real-time content capture of the real world and building a real-time 3D model, you can do this in a very immersive way. And this technology now is being spun out, actually. So we have this company, Dterm, which is here today. And if you want to try it and see it for yourself, go to the exhibit hall. And they've now built the infrastructure and hardware to do this real-time capture, and more importantly, semantic understanding. So once you've got that 3D model of the real world, what's a chair, what's a table, and so forth. So this is the hardware they built. It's a self-contained system with depth sensing camera and computer, and you can daisy chain multiple together, and then you can create a live 3D model of a much larger space, an office or a robot manufacturing facility or whatever else. So here's a video of this working. So this is one of their cameras. And if you break it open inside, you'll see there's a depth sensor, but there's also embedded computing with an NVIDIA platform that does all the data processing, and then you stream multiple together to create this 3D view. So you can try that on the show floor today. And the impression you should get from this is it's now possible to have a device that lets you capture in real time and stream in real time 3D models of the real world. And if you combine this, of course, with the other things I've shown you, you can now have people interacting and collaborating in that way, in a very natural way. So the three things I've talked about is implicit understanding and this trend from going from explicit to implicit input in XR, experience capture, and enhanced collaboration. And these all combine together in this field of research we're doing called empathic computing. And of course, underlying all of this is a heavy use of AI to make that understanding. So the goal of empathic computing is really, can we develop systems that allow us to share what we're seeing, hearing, and feeling with other people? So just like that experience I showed from SIGGRAPH, you really can feel like you're inside somebody else's body and experiencing their environment. And of course, in the show today and in the community, you'll see a lot of technology trends around better displays, real-time space capture, better gesture, eye tracking, and especially emotion sharing and sensing. And all this is kind of coming together into what you might call empathic teleexistence. And the idea of empathic teleexistence is you can change collaboration where people move from being an observer to being a participant, and they move from explicit to implicit communication, and they have this experiential of a collaboration, of a feeling of doing something together. So you really do feel like you're inside somebody's body, you're collaborating with them, and you're having the same experience. So that's what I want to talk about today. I've talked about this trend in the XR space from to implicit interaction, and we're now starting to see the first XR displays with integrated systems. And all this research is extremely complicated because we had to glue different things together, but now you can buy displays that have everything together. We've got this ability to work on empathic computing, and of course, there are many opportunities for research. You know, how do you build agents that can respond to your emotion? How do you share emotion? How can you monitor cognitive cues? And there's huge ethical and societal considerations. So if any of this is interesting to you, we're looking for collaborators. My research centre in Australia, we're number 2 in the world for AR research, number 19 for VR, and we're the largest AR VR research centre, academic research centre in Australia. So if you scan the QR code here, that'll take you to us. We have opportunities for students and also for industry. And then we've just recently started this journal. So if you're an academic and you're interested in this type of topic of collaboration and empathic computing, we've got this brand new journal. It's open access, and for the next 2 years, it's free to publish. So we don't have any charges as well. And then, of course, I've shown you a bunch of different research today. It's not my work, it's the work of all these people, my students and people in my lab. So they're a fantastic group. And if you have any questions, I would love to take some during the break, or you can contact me on email or Twitter or see the website for other projects. And I'm also happy to send you all the slide content as well. So just message me and say you're interested in the slides, and I'll get them to you as well. So thank you very much for your time, and I look forward to talking to you later at the conference. And please go and check out the D-term technology in the show floor later today. Thank you very much.